In Chapter 4, Section 11, we're going to be looking at alkanes, or cycloalkanes rather. And one of the things that we need to keep in consideration when we're looking at cycloalkanes is something that's called angle strain. Angle strain is when it's an increase in energy when the bond angles deviate from our optimum tetrahedral angle of 109.5. And sometimes it's quite obvious when we're going to have angle strain. If we look at something like cyclopropane, well, cyclopropane is going to have a lot of angle strain because the ideal angle at 109.5 is impossible with a triangle, or at least with an equilateral triangle like this. That angle should be about 60 degrees. And 60 degrees is a pretty significant deviation from 109.5. Even with cyclobutane, we're going to have a deviation of 90 degrees. With cyclopentane, we'd have 108 degrees, but then there's still some torsional strain that's involved there, and I'll show you that here in a second. When you get to the larger rings, like this one has, I believe, 10 carbons in it, you'll see that the angles get quite big. Although it can bend out of plane to avoid some of that, there's still going to be some angle strain with these larger cycloalkanes. We're going to find that the carbons will bend out of the plane. Now, of course, with cyclopropane, there's no way that can bend out because it takes 3 carbons or 3 points to make a plane, and so wherever those 3 carbons are, that is the plane. But when it comes to more than 3 carbons, 4, 5, 6, and so on, we'll find that they are not flat molecules. And the reason that they are not flat molecules is that they will pucker out of the plane in order to reduce some angle strain and or torsional strain. All right. And so here is a picture. You'll see even with cyclobutane, you would think it would want to stay as close to 90 degrees as possible because any puckering is going to cause those angles to decrease. Well, in order to avoid some torsional strain, it does pucker a little bit. Now, I've got a cyclopropane or cyclopentane rather molecule built here. All right, so here is the cyclopentane, and I've made it perfectly planar, or at least as perfectly planar as I can. If you look down any of the carbon-carbon bonds, you'll see that there is eclipsing at every single carbon-carbon bond. All right, so there's eclipsing at every single bond. So if we just take this molecule and bend it a little bit so that it is puckered. So now these 4 carbons are approximately in a plane, and this one is out of that plane. Well, now when you look down that carbon-carbon bond, you'll see that you get, it's not perfectly staggered, but you do get a little bit of staggering, and the same here, you get a little bit of staggering. Well, that's going to help to stabilize the molecule because we're avoiding some of that torsional strain. Remember, each one of those carbon-hydrogen interactions, each one of those is, when we're doing torsional strain, is worth 4.0 kilojoules per mole. And the carbon-carbon, let's find one, the carbon-carbon eclipsing is going to be worth even more. So by puckering it, we can get it out of that and avoid a little bit of that torsional strain. Now, going back over here, you'll notice the next one here is cycloheptane and cyclodecane, and even those will pucker out of the plane so that we can avoid some of the torsional strain and avoid some of the angle strain. You'll find that these, even these bigger ones like cyclodecane, you can see there's quite a bit of staggered interaction there, and the angles are much closer to 109.5, but it's still going to be strained because if you build this molecule as a molecular model, you'll find that you get some steric interactions between the carbons across the ring. You'll also notice that what's not here is cyclohexane, and that's because cyclohexane fits into a special category. So we're gonna spend a couple of sections looking just at cyclohexane rings. All right. So if cyclohexane were completely flat, we would expect significant angle and torsional strain, because if it were completely flat, the angles would come out to 120. If you have a regular hexagon, then the angles come out to 120, just like on benzene. So we would expect an angle of 120, which is somewhat greater than the 109.5, so that would give us some angle strain. And in addition to that, we would get torsional strain because we would get all eclipsing interactions. All right, so we would get all eclipsing interactions. Well, fortunately, we'll find that cyclohexane is not a flat molecule. It is chair-shaped. And so the shape that it takes, it looks kind of like a chair. And I've got a picture, or I've actually got a model of it built. So here is the model. And so this is the molecular model. This is the molecular model that is, I put this in the syllabus under materials. This one was optional. And if you ordered this, then you can check it out and try that out. But if you didn't order it, you should be able to get by without it. But if you look here, we've got, this is one part of the chair, and then here, this is sort of the back of the chair. So like here is our back of the chair. There's sort of the foot of the chair. And then these are the sides of that chair. And that is that. All right, and we'll find that if we look down any of the carbon-carbon bonds, and let me see, it's a little weird arranging it for this. So if we look down any of the carbon-carbon bonds, we'll see that they are all staggered. We'll also see that the angles will all come out to 109.5 degrees. All right, so all of the carbon-carbon bond angles come out to 109.5 degrees, and all of the hydrogen and carbon atoms end up being staggered. So cyclohexane is unusually stable compared to the other cycloalkanes. Now, it's not stable as compared to just a regular alkane. It's about the same, but compared to the regular alkanes, or compared to the other cycloalkanes that have the angle strain, this is much more stable. All right, so we want to look at what we refer to as axial and equatorial positions. So in each carbon in the chair has two different kinds of hydrogens. And those two different kinds of hydrogens are axial hydrogens and equatorial hydrogens. And so here is a picture of a model, although I am going to, again, switch over and show you my model. All right, and so I've made it so that the axial hydrogens in this model are red and the equatorial hydrogens are white. You'll notice that when I set the model down, when I set that model down, the red ones go vertical, so they're straight up and down, and the white ones are going out away from the carbons. So the axial ones are hydrogens that are located above and below the ring, and they are perpendicular. They're in the perpendicular axis, so they're going straight up and down. And then the equatorial are approximately in the plane of the ring around the equator. Now, they're not literally in the plane because, they're still the 109.5 degrees, so they're not perfectly in the plane. But you will see that they are approximately within that plane. All right. When we draw this, we're going to differentiate between the axial and equatorial hydrogens with the way that we draw it. So over here is a drawn cyclohexane ring in the chair conformation, and I want to get this so that it approximately looks like what you're seeing on the screen. All right, so there it is. And so here we've got those two sides, and that's going to be here and here. And then the hydrogens, let me pick this one. So this hydrogen is this one that is pointing up, and the hydrogen, I'm holding on to my equatorial hydrogen there. It's right there. It's kind of hiding behind this hydrogen. So you can see that the ones that are pointing up are axial, and you'll want to, when you draw the molecule, you want those to point directly up or down, depending on whether they are on the top or on the bottom. And then the equatorial ones are going to be at an angle that's approximately 109.5 degrees. And so that is how you draw it. Now, we're going to practice drawing that here in just a few seconds. All right. This is what that model looks like in terms of what it looks like when it's the ball and stick version of the model. All right. So now we want to practice drawing cyclohexane. And when we're drawing the chair, the first thing that we want to do is to draw the side parallel lines. And so here I've indicated there are these side parallel lines. Then you want to draw the top and bottom parallel lines. And so you'll start at this point and draw one that kind of comes in over here and one here that comes this direction, and they will be parallel. So they are parallel. They're not right next to each other, but they are definitely parallel to each other. And then finally, we're going to connect this point to here and this point to there, and that will complete our cyclohexane ring. So that will complete our cyclohexane ring. Once you've got the cyclohexane ring drawn, then we want to be able to put in axial and equatorial. So to do this, you need to recognize that there's three different types of carbons on the cyclohexane ring. There's ones that are up on top, so this one, and this one. Those are up on top. And there's three that are down on the bottom, so 1 and 2 and 3. Those are on the bottom. We'll just call those up and down carbons. All right. And so you'll go to the up carbons and draw a line directly up from that. And then you'll draw a line that's directly down from the down carbons, and then that will be your axial hydrogens that you put in. So that'll be your axial hydrogens. Sometimes the hydrogen here will be in front there, and you just kind of have to be creative about how you draw that, but that is what that one looks like. You'll see this one is in the back, and it's pointing straight down. So those are our axial hydrogens. And then our equatorial hydrogens, we'll just come in and put them at approximately a 109.5 degree angle here, there, and then here and there. And then for this one, the one that's on the left, you'll kind of come over here to the left, and the one that's in the back there, it'll kind of go back into the right. So we'll draw those in at approximately 109.5 degrees. Now, while we've got that there, I'm going to come back over and show you what this looks like, and so you can compare the structure that you see over here on the right side of the screen versus this structure. And again, the red ones are axial and the white ones are equatorial, and that kind of gives you an idea of what everything looks like. Okay. So now that we've done that, we're going to practice drawing the cyclohexane rings. All right, so let's switch over to our document camera here. All right, it says practice drawing the chair conformation of cyclohexane. So practice drawing that. So again, draw your two parallel side lines, and then you'll draw a line here and there. Those are parallel, and those are your front and back. And then you'll just kind of connect those. You'll connect it a little bit better than I did. It does take a little bit of practice to do this. So that is just one of them. Let's do another one. And I'm going to encourage you, after I'm done with this little section, to pause the video and practice doing this yourself. All right, so there is another one. And it doesn't have to be perfect, but it does need to convey what's going on. So it does need to convey what's going on. All right, on this one, let's put in some axial and equatorial hydrogens. So here I'm going to put in an axial, I'll just put in the axial position. So there's one there. Again, here's the carbon that's up. All right, and then the ones that are carbons are down, those are all our axial positions. And then just go in and put in your equatorial positions. And again, just try to make about a 109.5 degree angle there, 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 and there. And then for this one that is in the front, kind of have it come off this way, and the one that's in the back, just kind of have it go back that way. I'm going to bring up this model again, and so you can compare what this looks like. Get that pen out of the way. So you can compare what that looks like to what we just drew. And it looks pretty close, right? So the red ones here, and that one's a little off kilter. So that the red ones, okay, the red ones are axial positions, and the white ones are the equatorial positions. So practice doing that, get really good at it. One other quick thing that I want to mention is that we're going to be drawing the ring when it tilts the other way as well. So you'll want to practice that as well. So parallel lines going that way. And so that would be a cyclohexane ring as well. All right. And you can kind of adjust this to make it a little more open. Here we've got it so that it's that it looks really, all right, so it looks really kind of closed there, but you can open it up a little bit if that will help you to see it a little bit better. So just experiment with it, but you want it to look something approximately like this. And again, always go in and you can designate your positions, the axial positions, go to the points, and if it's an up point, which is every other one, you'll just go straight up from there. And for the ones that are down, you'll go straight up. You'll go straight down from there. Now, one thing that I want to discourage you from doing, all right? So here I'm going to draw one, and I'm purposely going to mess it up. And let's kind of get that out of the way. I'm going to purposely mess it up, and so I'm going to put it in a different color. So everything looks good here, and these are things that I want you to avoid. So coming along here, and you say, oh, that one is, I'm going to put a vertical position in. All right, don't ever do that. So don't ever do that. You'll make sure you put them at the point. Wherever the point is, go up from there. And if the point's going down, then go down from there. Don't do this. Other things I don't want you to do is I don't want you to just do it at an angle like that, right? Our true hydrogen is going to go vertical. Our other one's going to go this way. This one, I can't tell where it is. So this is bad. All right, and I'm going to put an exclamation point to indicate that that's bad. So both of those things are bad things to do. And I see this all the time, and this is kind of like, I don't know, that's kind of like if you had your hand and your fingers went back the other way, well, that would look really strange. That's not how it's supposed to look. All right, so I'm not going to draw anymore, but I want you guys to pause the video and practice drawing these cyclohexanes, practice drawing in the axial and equatorial positions. And of course, we're going to do stuff like put hydrogens in on these. And here in a few minutes, we will be doing stuff like putting in other substituents. All right. So I'm going to want you guys to pause it just for a bit. All right. So now that you've practiced doing that, we're going to look at something that we call ring flipping. And so ring flipping is where we flip the ring. We change it from one chair conformation to another chair conformation. So again, we call that a ring flip. When we do a ring flip, the up carbons will end up becoming down, and the down carbons will end up becoming up carbons. And so this is what the ring flip looks like when we're drawing the chair without our positions drawn in. And so here we've got a chair over here on the left. We're going to bend up this one. All right, so we're going to change the conformation and bend it up. It will temporarily be in what is called a boat form. And the boat form is much higher in energy than our chair conformation. And then this one is going to flip down, and it's like we've flipped the chair over, and what was the head is now at the foot of the chair, and what was the foot is now at the head of the chair. All right. We're going to find that when we do a chair flip, it interconverts the positions on the ring. So what was any axial hydrogens that you have become equatorial hydrogens, and any equatorial hydrogens become axial hydrogens. So here is the chair cyclohexane, and you notice it's drawn a little bit strange here, but that looks like the chair that we've been drawing. And you'll notice that we've got half of the hydrogens that are blue and half of them that are white. Kind of like on the picture that I showed you a minute ago, I made half of them red and half of them white. Well, when you do the chair flip, something interesting happens, which is all of the axial hydrogens become equatorial, and all of the equatorial hydrogens become axial. All right. We will find that that equatorial position has more room than the axial position. So typically larger substituents, anything larger than hydrogen, is going to be more stable in that equatorial position. I'll show you why that is the case here in just a bit. But before I do that, I want to show you this model. All right, so here is our cyclohexane that I had shown you a little bit earlier. So there it is. Okay, and we're going to do a chair flip. So I'm going to take this one right here and pull it up, and then take this and pull it down. And you'll notice now that all of the white ones are axial. And let me get that so that it looks like a chair for you guys. So you'll notice all of the white ones are axial and the red ones are equatorial. So we've switched positions. We've switched positions for the axial and equatorial. Again, pull that one up and this one down, and you'll see that now the red ones are back to axial. Well, it turns out in regular cyclohexane, it flips back and forth many times a second. So it's constantly going back and forth. So it is constantly going back and forth. Again, there is a barrier to rotation when it's doing this, but as long as there's some temperature, some amount of heat that's involved, then it can flip back and forth. So let's take a little bit closer look at that boat conformation. We'll find that the boat conformation is about 30 kilojoules per mole higher in energy than the chair conformation. So the chair is 30 kilojoules per mole more stable. That means that cyclohexane spends almost all of its time in the chair position. It just goes through that boat position just ever so temporarily, so that we can get from one chair to the next. All right, so this is what that boat position looks like, and here you'll see what are called flagpole hydrogens. I'm going to go back to our picture, our model here, and on this model, I'm going to flip this up, and it will now become a boat position. And so these are the flagpole hydrogens. If you look down the carbon-carbon bonds, all right, so let's look down this carbon-carbon bond. You'll see that you've got eclipsing interaction. So this carbon hydrogen eclipses this one eclipses that one, this carbon-carbon bonds eclipse. And so in reality, you'll find that it really won't stay in that boat conformation. It's actually going to do something where it's called a boat twist. And the boat twist, it just twists a little bit out of the plane, and in doing that, it gives you more of the staggered interaction. So this is actually significantly lower in energy than the strict boat. So it doesn't spend a whole lot of time there, but it does spend a little bit of time in our boat position. These flagpole hydrogens, that's one of the reasons it doesn't stay there, because there is a little bit of steric interaction, particularly if you have larger groups there. And then we can flip back over and give us the other one. I'm not sure which one I started with, but there we've got axial reds, and here we've got axial whites. All right, so that boat conformation is going to be destabilized by torsional strain, and as I mentioned, you get what's called a twist boat when you are in that boat conformation. We'll find that there is a little bit of steric strain between the flagpole hydrogens. All right, so now we want to look at substituted cyclohexanes. With the substituted cyclohexane, we'll find that the two conformations are not equally stable. One of those conformations is going to be more stable than the others. We'll find that that when we have axial substituents, particularly if they're large, we're going to create some destabilizing 1,3 diaxial interactions. I'll show you what those are here in just a moment. We'll find that for methyl, each one of those diaxial interactions is worth about 3.8 kilojoules per mole. So here, this is where we have a CH3 group that is equatorial, and over here on the right, when we do the chair flip, well, anything that was equatorial is going to become axial, and anything that is axial is going to become equatorial. Now, going back to this picture here, I've got the substituent A, or the conformation A, that is over here on the left side of your screen. And so here we've got the methyl substituent that is in that equatorial position. And we're going to do a chair flip. So we're going to bend that one down, bend this one up. And now you will see, I'm going to get it so it looks just like what you have there. Now you're going to see that you've got, just trying to get the right angle there, that methyl is in an axial position. All right, and so it switched. So again, the red ones were equatorial and the white hydrogens were axial. When we flipped it, now the red ones are axial and the white ones are equatorial, but what also flipped was this methyl group that is right there. All right. Well, the 1,3 diaxial interactions that I was talking about, I'm going to flip this over so we can look at this. The 1,3 diaxial interactions are the interactions that are between this methyl group and the hydrogens that are 2 carbons away. So if you call this carbon 1, carbon 2, carbon 3, then that would be a 1,3 diaxial interaction. Now on this kind of model, it's a little bit more difficult to see that, which is why I'm going to switch over to this kind of model. So the ball and stick model type of model is a better illustration for why we get these 1,3 diaxial interactions and why those steric interactions will destabilize. So here is our equatorial position. When we do the chair flip, we end up with an axial position, and that axial position has steric interactions. All right, so we're going to do some chair flips with that here in just a few minutes. Okay, the larger the substituents are, the less favorable the axial interaction was. You may or may not remember here. I'm going to go back a couple of pages here. The percentages here are approximately room temperature. You'll find that the equatorial position makes up about 95% of the at the sample at any given time, and the axial position makes up about 5%. And that's due to this 3.8 kilojoules in difference. The bigger that number is, the bigger the percentage difference is. Well, if we get a bigger interaction here, so let's say we get something like tert-butyl. The tert-butyl group is essentially 100% equatorial conformation. All right, so the tert-butyl group is essentially 100% because that tert-butyl has a much stronger 1,3 diaxial interaction. It's much more than 3.8 kilojoules. It's big enough that it's about 99.9999 something percent of this, and such a small percent of this you can't even really measure it. All right, so that the bigger the group is, the bigger the difference in the percentage. If you had ethyl, and so instead of 3 CH3s on this carbon, you just had 1, then it would be somewhere in between that 95 and 100%. All right. Now we want to look at disubstituted cycloalkanes. So when we have 2 cycloalkanes, we have 2 substituents on the cycloalkanes, not just 1. When we have disubstituted cycloalkanes, we will find that there are 2 ways that you can arrange the substituents on the ring. Well, there's multiple ways because you can put them on different carbons, but let's say we're just putting them on adjacent carbons. So we're going to look at the molecule 1,2-dimethyl cyclopentane, and you'll see that there are 2 ways that we can put those methyls onto the ring. If we put them so that they are on the same side, we call that the cis isomer. If we put them so that they are on the opposite sides, we call that the trans isomer. So cis and trans are the words that we prefer to use here. The cis isomer, again, same side, and the trans isomer, opposite sides, are referred to as stereoisomers. In the next chapter, we're going to be talking about a variety of different kinds of stereoisomers, but we're in this chapter, we will just say that those are stereoisomers. They have the same connectivity, but the atoms are oriented differently in space. Now, to show you this picture, I have some molecular models that I've built. And so here, this represents the cis isomer. And so you'll see that we've got all 5 carbons. And then we've got the hydrogens that are here in the back, and you'll see those 2 methyls are coming up towards you. And so that is the cis isomer. For the trans isomer, get that arranged. For the trans isomer that's over here, so this carbon, we have the methyls that are coming up, and that's that methyl that's coming up towards you. And then down here, we've got this methyl that's pointed away, and you'll see that when you look at it from the side, they're clearly on opposite sides of the ring. So we've got these trans isomer, they're on opposite sides of the ring. Well, these 2 molecules, like I said, they are stereoisomers of each other, and these stereoisomers actually have different properties. Now, they're both cycloalkanes, and so they're both combustible and that kind of thing. But we will find that they almost certainly have different boiling points, different melting points, and possibly they can have slightly different reactivities. All right, so cis and trans. Now, when we draw rings like this, we assume that the rings are going to be planar. Even though we know that the molecule itself is not planar, that this is going to pucker a little bit to get to reduce some steric strain in the case of the cis isomer, and also some torsional strain. But for purposes of drawing them like this, we're just going to pretend for a moment that they are in the plane. All 5 of those carbons are coplanar. Same thing with the trans isomer. And the reason we do that is that's an easy way to draw rings that have stereoisomers. When we do this with the cyclohexane, disubstituted cyclohexanes, well, we're going to find that, again, that there are, we can draw it so that we have a hexagon, and then we simply draw wedges to indicate whether they are on the same side or opposite sides. So here we've got the trans isomer of 1,4-dimethyl cyclohexane, and then here's the cis isomer of cis 1,4-dimethyl cyclohexane. All right, and we'll find that each one of these has 2 possible chair conformations. So each one will have 2 possible chair conformations. All right, so let's start with the trans isomer. All right. Well, and then before we do that, I want to go over with how we map chair flips. Which carbons are which when we're doing a chair flip? Now, the numbering on this is a little bit arbitrary, but I recommend using this number system as a way to help you keep track of where everything is. So this carbon is carbon number 1, and it will become the carbon that's pointing down. You'll notice that all the carbons that are pointing up, 1, 3, and 5, that those will be the carbons that are pointing down in the chair flip. So 1, 3, and 5 are pointing down. The ones that are pointing down over here, 2, 4, and 6, will be the carbons that are pointing up over here. If you can remember this map, this mapping system, then you're going to save a lot of trouble and you will get more answers correct on the test and you will understand the concepts better if you do it this way. So just trust me, and we're going to practice doing this here in just a second. So let's look at that trans. So we're going to do the trans isomers. So the trans 1,4-dimethyl cyclohexane. So this one is trans. When you have substituents on the ring, there's always going to be a substituent that is up and one that is down. And on carbon number 1, the one that is up is in an axial position, and the one that is down is in an equatorial position. On carbon number 4, which is over here, the one that is up is in the equatorial position, and the one that is down is in the axial position. So when you have trans, you'll have one substituent that's up and one substituent that is down, and that's what's going on with this particular ring. All right. When we do the chair flip, well, the 1 will come over here, the 4 will go up there, 2 and 3, we don't have anything on 2 and 3 or 5 and 6, but we might here a little bit later. We definitely will when we do a couple of these problems. And so when we do that, we want to be aware of where everything goes, and we need to practice this a lot, and we want to make sure that we remember that whatever was in the axial position, this hydrogen, ends up in the equatorial position in the chair flip. What was in the equatorial position, this carbon, ends up in the axial position over here. So if you can remember the mapping and you can remember that they have to switch positions from axial to equatorial, you're going to do much, much better. So let's look at what this looks like with the trans 1,1,4. That's not 1,2, 1,1,4. All right, and with a quick pause, I fixed that error. So it's trans 1,4-dimethyl cyclohexane. All right, and so the two conformations are not equally stable. Here, you'll notice on the first conformation that both of our substituents are in the equatorial position, which means when we do the chair flip, both are going to be in the axial position. Well, those ones in the axial position will make this conformation less stable. So the conformation with both substituents in the equatorial position are much more stable than the other one. All right, so let's switch over to number 57 on the in-class assignment. So it says, draw the two possible chair conformations for cis 1,4-dimethyl cyclohexane. So up here, I'm going to draw in this format the cis, so CH3, CH3. All right, so that is our cis 1,4-dimethyl cyclohexane. And we're going to start, I'll just number this arbitrarily. I'll call this one 1, 2, 3, 4, 5, and 6. And so now we want to draw our first chair conformation. Okay, so do our sides, our top, and then these connecting bonds. And again, start with this, call this one 1, 2, 3, 4, 5, and 6. We're only going to be putting things at positions 1 and 4. So that'll be pretty easy. I'm going to move my camera in just a smidge. All right. So now let's put anything that is pointing towards us, we're going to call that up. So it's kind of like we're taking this and we're setting it down and looking at it from the side. So the 1 goes there, the 2 is going to come out front, this 3 will come out front, the 4 will be on the side here, 5 will be in the back, 6 will be in the back. So whatever is in front on this view is going to be on top. So we're going to have a CH3 that is in the axial position and a hydrogen that is in the equatorial position on carbon number 1. For carbon number 4, well, we've got a CH3 that's coming up. If we look, so there's our axial and equatorial. Up is going to be the CH3. So our CH3 there ends up in the equatorial position, and our hydrogen ends up in the axial position. So now let's do our chair flip. So we'll get the rapid interconversion between this and our chair flip. For our chair flip, we're going to draw the opposite angle on our sides, and then our parallel lines that go there connect, our bonds there. And then let's go ahead and number it. So again, this is 1, 2, 3, 4, 5, and 6. Now again, 2, 3, 5, and 6 aren't going to matter much here, but let's go ahead and put in our axial positions on 1 and 4 and our equatorial positions at about a 109.5 degree angle. All right, what was axial here in the chair flip is going to become equatorial, and what was equatorial will become axial. So that will be in the axial position. Now, what was equatorial on carbon number 4 is going to become axial after the chair flip, and what was axial becomes equatorial. All right, so now it says, which conformation, if either, is more stable? Well, if you look at this, you'll see this one has one methyl that's axial, one methyl that's equatorial. This one also has one methyl that is axial, one methyl that is equatorial. So these should be equal in energy. That means that we should have about half of it in this conformation and half of it in this conformation. All right, so let's go back to the presentation real quickly. And so this is the cis, and this is exactly what we drew. So here is our cis conformation. So one is up, and they're both up actually because they're cis to each other. And we will find that you have one axial, one equatorial, and then over here we've got one axial, one equatorial. So in the cis isomer, the substituents on the same side of the ring, so they're either both up or both down. In this drawing, I've made them both up, but you could have made them both down. That would have been completely legit. And so we'll have, that means both of these are equally stable. Okay, so now we want to go and look at number 58, 61, and 65. And things are going to get a little bit interesting when we do this. All right, so here on number 58, all right, so here on number 58, we are going to, let's see, we have the cis 1,3-dimethyl cyclohexane, and so let's go ahead and draw that. And since it's cis, that means they're same side. So we're going to call this one 1. So there's a CH3 there, and then this 2, 3, and so there's a CH3 there. And it will go ahead and number this 1, 2, 3, 4, 5, 6. Okay. And now we want to do just exactly the same thing we did a little bit ago, except except we're going to have those methyls in slightly different positions. All right. After you've practiced drawing this enough, you will get much faster at this. 1, 2, 3, 4, 5, 6. All right, again, anything that's coming towards us in this picture is going to be up. So on carbon number 1, we'll have one that is up, CH3, and the hydrogen is going to be down, and so that's going to be in the equatorial position. Now let's look at carbon number 3. So carbon number 3, our up substituent is there. That's going to be methyl, so CH3. And then our equatorial position, this is a common mistake. Equatorial position, you want this one to come out this way. I see students draw it this way a lot, and I think the best way to prove to you that this really works is well, let's just see here. I'm going to do more. Okay, so let's get it. So we've got, it looks like a chair. All right, so there is the chair. This is not the exact chair that we have, but it's pretty close because we've got the methyl here. Here, this red one would also be a methyl. But you'll notice that this equatorial position that's on carbon number 3, so this is carbon 1, 2, 3, 4, 5, 6. On carbon number 3, the equatorial position is kind of going off to your left. So it's going to look like that. All right, so there we go. We have hydrogen there and there. Well, clearly these are both axial, so this is probably going to be our less stable conformation. Well, not probably, definitely. So now let's do the chair flip. Remember with the chair flip to tilt it the other direction. All right, and I'm going to go ahead and number it. 1, 2, 3, 4, 5, and 6. Okay, so here this methyl on carbon number 1 is in the axial position, and so in the chair flip it's going to be in the equatorial position. Our hydrogen, which was equatorial, will become axial. Now for carbon number 3, here's our axial position, and there's our equatorial. So the hydrogen was equatorial, it's now axial, and the CH3, the methyl, was axial, and so now it is equatorial. And then which one is more stable? Well, the one that has two substituents in the equatorial position. So this one is more stable. All right, so again, those are both the same compound. It's just that it's chair flipping back and forth. It's going to spend the vast majority, probably 99% plus of its time in this equatorial position, hardly any of it in the axial position. All right, so which of the given 1,3,5 trimethyl cyclohexane isomers is more stable? Explain your choice. So on this one, what I'm going to recommend is, again, just numbering it. We're going to number this 1, 2, 3, 4, 5, 6, and then we'll number this one the same, 1, 2, 3, 4, 5, 6. These are stereoisomers of each other, so they're both 1,3,5 trimethyl cyclohexane. However, one of them has a different orientation in space. So let's do this. We're going to call this one compound A and this one compound B for purposes of keeping track. So we'll do compound A first. All right, so let's do our chair isomer. Draw our chair. I've been doing this for decades, and I sometimes will mess up my chair. So if you mess up a chair, just either cross it out or get yourself some correction tape and draw it again. All right. Just like what we were doing, let's do this 1, 2, 3, 4, 5, 6. And that way we can keep track of where each of those are. Since these are all coming towards us, we're going to make those all up. So we'll put our up and down positions at carbons 1, 3, and 5. And so the ones that are coming towards us, those are up. So we'll have CH3 and then hydrogen, and then CH3 there, also in the axial position, and hydrogen. And on carbon 5, CH3, also in the axial position, and the equatorial will be hydrogen. Well, clearly this one is not going to be very stable in that conformation. So we're going to do the chair flip for this. All right, so we'll do the chair flip. And again, when you're doing this, I encourage you to number it. So 1, 2, 3, 4, 5, and 6. Let's just go in and draw your axial and equatorial before you even worry about which atoms go there. So we'll put our axial and equatorial on carbon 1. On carbon 3, we'll do axial and equatorial. And then on carbon 5, we'll do, there's an axial and equatorial here. It's going to go kind of back and to the left. All right, so all these things that were axial are now going to be equatorial. So we'll have CH3, CH3, CH3. And all these that were equatorial will now be axial. All right, and clearly this is the more stable conformation. So now drawing the next one isn't too bad because we've already done quite a bit of the work here in identifying where these are. The only thing that's going to be different, so here we've got axial, 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 axial. Well, this one's going to be axial, axial, equatorial when we do this particular conformation, so this particular chair. Made a little bit more room in that chair so we can see it a little bit more clearly. All right, so let me put the numbers in. 1, 2, 3, 4, 5, and 6. So here we're going to put our axial and equatorial positions on carbons 1, 3, and 5. On carbon 1, we've got CH3, hydrogen. Since that one's coming towards us, it's up. This one's coming towards us, so it's also up. And then on carbon 5, that one's going away from us, so it is down. So that CH3 is in the equatorial position. So we'll find that this particular isomer, or this particular conformation rather, is a little bit more stable than this conformation, but we need to look at both conformations. So now we'll do the reverse, which is going to give us our chair flip. All right. Again, I encourage you to map it out. So 1, 2, 3, 4, 5, and 6. All right. We'll also go ahead and put our positions in at 1, so our axial and equatorial there. At 3, axial and equatorial. And at 5, axial and equatorial. Okay, so this one, methyl was axial. It becomes equatorial here. The hydrogen was equatorial, and now it's axial there. For carbon number 3, our axial is methyl, so that becomes equatorial over there. And our hydrogen was equatorial, so now it is axial. Carbon 5, it's the reverse. So carbon 5, the CH3 was equatorial, so here it is axial, and the hydrogen was axial, so now it becomes equatorial. So on this one, we've got one axial substituent. That one axial substituent will have 1,3 diaxial interactions, and so that makes this a less stable conformation than this. And that means that our top one, this is a more stable isomer because it has the more stable conformation. Remember, even though this is really unstable, well, the molecule doesn't spend any time in that conformation, or hardly any of the time in that conformation. So it's going to spend the vast majority of its time here. So this is going to be more stable because all three substituents are equatorial. All right, so we now want to look at 65. Let's see, 65. All right, and here we're looking at different kinds of isomers. Okay, so here, that didn't show up very well. That is just cyclobutane. So in case you have trouble printing that out, that was just cyclobutane. So we want to determine whether these are constitutional isomers, which means different connectivity, stereoisomers, which means same connectivity, different arrangement in space, identical molecules, which means exactly the same molecules, or not isomers of each other. All right. Well, the easiest thing to do when you are trying to determine if these are constitutional isomers, stereoisomers, identical molecules, or not isomers. Well, all right, so constitutional isomers have different connectivity but the same chemical formula. Stereoisomers have the same chemical formula, same connectivity, different orientation in space. Identical molecules have same connectivity, same chemical formula, same orientation in space. And then finally, not isomers is going to have a different chemical formula. So first, let's look, does it have the same number of atoms? So 1, 2, 3, 4 carbons, so that's good. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, 2, 4, 6, 8 hydrogens on that. So these have different connectivity, but the same formula. These are constitutional isomers. So those are constitutional isomers. All right. And again, so same formula, different connectivity. All right, my word got a little messed up there, but same formula, different connectivity. Now for this one, we can clearly see that these are the same formula. This is a cyclohexane with 2 methyls at positions 1 and 2. This is a cyclohexane with 2 methyls at position 1 and 2. So these have the same formula, the same connectivity, but we'll see that they have different orientations in space. So these are stereoisomers. All right, so again, same formula, same connectivity, all right, different orientation in space. So that's our hallmarks for stereoisomers. All right, let's look at this one. So we've got a cyclohexane ring with 2 methyls, and they are, let's see, they are trans to each other because they're on opposite sides of the ring. And then here we've got a cyclohexane ring, but it's drawn in a chair conformation. They are 2 methyls, and again, they're at the 1 and 3 positions, just like this one. So these are also trans to each other. All right, so if we look, let's say we number this 1, 2, 3, 4, 5, and 6. All right, and this one I'm going to number a little bit different than I have on the other things, but again, the numbering is arbitrary. So 1, 2, 3, 4, 5, and 6. If you look, this one, the methyl is up. Here, the methyl is up. It's higher than the hydrogen. This one, the methyl is down, and this one, the methyl is down. It's trans. These are identical molecules. They are just drawn differently. So those are identical molecules. So same formula. Same connectivity. All right. And same orientation in space. All right. So now let's look at this next one. At first glance, let me move that down a little bit. At first glance, you'll say, okay, so we've got a cyclohexane. This has an ethyl and ethyl. This one's cis, and this has an ethyl and an ethyl. That one's trans. These must be stereoisomers of each other. Well, that would be wrong because this one is a 1,3 isomer, and this one's 1,2. So these have different connectivity. So these are constitutional isomers. So those are our constitutional isomers. Again, same formula. Different connectivity. All right. And once you get that different connectivity, it doesn't matter. It doesn't matter at all that this one's cis and that one's trans. These are just, they're constitutional isomers. All right. So this one, we've got cyclohexene. So C6, let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C6H10. And then here we've got 6 carbons. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12. And these are not isomers. And that's because they have different formulas. All right, so those are not isomers of each other. Okay, so let's go back, and we just have one little section left on this. And the one little section that we have left is looking at oxidation of alkanes. We have a whole chapter on oxidation and reduction. Generally speaking, though, the more bonds that you have, oxidation occurs when you increase the number of bonds between carbon and something that's more electronegative than carbon. For example, between carbon and oxygen, or between carbon and a halogen. Those are common examples. So if you increase the number of bonds between carbon and something that's more electronegative, typically you'll find that it's getting oxidized. We'll also find that oxidation results when you decrease the number of carbon-hydrogen bonds. And so with a if you decrease the number of carbon-hydrogen bonds, then we will say it has been oxidized. Reduction will occur when you either decrease the number of carbon bonds with something more electronegative, or if you increase the number of carbon-hydrogen bonds. Now, we'll talk about oxidation states and that more, but the more bonds with oxygen, the more oxidized it is. So here you'll see there's 4 bonds with hydrogen and no bonds with oxygen. This one has 3 bonds with hydrogen and 1 bond with oxygen. This one has 2 bonds with oxygen, 2 bonds with hydrogen. This one has 3 bonds with oxygen, 1 bond with hydrogen, and this one has 4 bonds with oxygen. So this is the most oxidized form of carbon, at least with oxygen, and this is the least oxidized. It would have the lowest, the lowest oxidation state. So this would be the most oxidized, that would be the least oxidized, or the most reduced. All right. Now, there are intermediate steps. If you have bonds with carbon, then a bond with carbon is somewhere between a bond with hydrogen and a bond with oxygen. Again, we'll talk about that more later, but this is a good first step for understanding oxidation of alkanes. Whenever you burn something, you'll find that the more bonds you make with oxygen, then the more heat you're going to release when you burn it. Or, I'm sorry, the fewer bonds that you have with oxygen, then the more heat is going to be released when you oxidize it. Because when you burn it, you convert it all into carbon dioxide. So if you burn an alkane and you burn it in the presence of oxygen, you produce carbon dioxide and water, then you will produce some heat. So methane, that's a component of natural gas. When you burn it in oxygen, you will produce carbon dioxide and water. Here, this is isooctane, which is a component of gasoline. And you'll see here that we've got all these carbon-carbon and carbon-hydrogen bonds. We oxidize it and we produce carbon dioxide and water. And in both of these, heat will be produced. So generally speaking, the more oxidized you make the carbon, then the more heat you're going to generate in that reaction. And that's all to that last section. It's just sort of an add-on section that's kind of interesting. As I mentioned, we will be looking at oxidation reduction in a lot more detail in a later chapter. And that, complete carbon. All right, and that is the end of chapter 4.